So to kick off this 30-minute final video, I'll start by walking through my scene and showing off the necessary features, and then I will step through the code afterwards to explain how I have everything set up. So before building the scene in DirectX 11, I did a quick blockout in Unity as a prototype. I used it mainly for fast iteration testing model scale, UVs, and rough placement using the editor tools and gizmos. It let me experiment without needing to recompile every time I made a small change. I didn't transfer any positions directly though. Once I had a general sense of layout and composition, I then rebuilt everything from scratch in DirectX 11, starting from the terrain height map and skybox. So starting off the scene, I placed the camera outside of the graveyard to create the idea that the player has been walking for a while and just discovered this area. I have 4 candles in the scene, 3 of which move dynamically, and they all have point lights attached to them to demonstrate the lighting in the scene. And then moving into the graveyard, I have a mausoleum on the left and tombstones in the back and trees scattered both within the graveyard and in the terrain outside. Any trees outside the graveyard are placed using a XZ sampling method to get the Y value of the terrain height map, and then place the trees according to the height of the terrain. And then trees inside the graveyard are placed manually. One useful thing I discovered during my Unity prototyping phase was that my 4 tombstone meshes only need 2 textures, which simplified my setup when I implemented them in DirectX. I also implemented a distance-based fog to the necessary shader files and set the appropriate settings to create a sort of snowy fog effect that doesn't completely cut off the skybox from view. And then I also made sure that if no settings are passed to into the fog, it doesn't do anything, since it did wash out my scene the first time I tried it. I also have 8 static spotlights in the scene, although they are primarily used to simulate moonbeams and add depth to the scene. They're meant to act as fake god rays / moonlight that's peeking through the clouds in tandem with the skybox, and I have them all scattered around the graveyard and sparsely on the edges and in the background. And then there is a directional light for general lighting, although it is dimmed to show off the point and spot lighting. And then the tombstones are placed using a looped grid setup that also randomizes which tombstone object is placed, and then they are manually offset on their heights using a 2D array to match the terrain heights. This was before I created the XZ terrain height sampler for the trees. And then with that placement loop, and then within that placement loop as well, there's some logic to handle rotationally offsetting the graves randomly to give them a more worn down and aged look. And then hiding around the mausoleum is my pile of demo objects to match the criteria. I have 2 crates, a dice, a pyramid, a sphere, and the cottage. Since I couldn't really find any good models with at max 4 meshes, most models I found either had 1 solid mesh or 20 to 30 tiny meshes. So I hope this is okay to show that it is at least functional with 4 unique textures assigned to it. And then finally I have the fence objects surrounding the graveyard, defining the general area. And this also just uses a set of loops to place objects, starting at different XZ positions and offsetting the next model placement a certain amount of units to construct a fence perimeter. So now looking at the code of how the scene is set up, I'll run through the methods and pointer declarations within the dxapp.h file, and then move into the .cpp and work from the top down. So I have a list of helper methods that I use to help condense the .cpp file. I'll just give a brief explanation and then I'll get into them later. But this creates a custom candle model using 3 cylinder shapes. And then this updates our 3 dynamic candles. This one updates the 4th, I guess, candle that's orbiting the demo objects. This adds our list of, this just adds 1 moon spotlight with set parameters where we only have to pass in position and direction. Candle point light, similar, only pass in a position and then a diffuse since we kind of flicker them over time. Render crate just places it in the world. Render tree, similarly, this has a little extra method to it to randomize the trees a bit. Generate grid positions just kind of creates a list of positions that we then render from. This just kind of loops through a list and renders the graves. And then same thing with the fences. And then terrain gets its texture pointer, same with skybox, fog settings. And then each object is its own graphics object's texture light with a model and matrix position. Everything should have its own matrix position, otherwise I use a list for like multiple repeated objects. And then, yeah, same down here. Moving lights and spotlights. And then some, I guess, further helper methods. Yeah, this just writes the spotlight positions because I have them preset, so it just writes them to a list in init demo. And then same with background, or no, this one is a custom helper method that I'll get into in a second. And then this one is manually placed positions in a list. So nothing too fancy there. So moving into init demo of dxapp.cpp, I set up a list of static scene constants to apply scale, rotation, transform values for each object, as well as material properties to send with the object. This way, anything static and not updating remains untouched after the initialization of the scene. And then we set up the shader texture light to be used for objects in the scene. Originally, I had both color light and texture light both in the scene, but transitioned to only using just the texture shader light for simplicity, or shader texture light. After that, we create the texture for our terrain object and then pass that in along with a height map and some parameters to control the size and texture tiling of the terrain object. And then we set the material as well. After that, we create next is the skybox, which also receives its own texture and is given that during creation within adjustable scaling size that we have just set to 500. And then we define our fog settings, which eventually get passed into the shader within the draw scene, but this keeps them static and stable inside the init demo. Yeah, that's fine. And then just to show that if you have those not set, the scene doesn't blow up. Then we define all the models to be used in the scene. We have the required unit box with repeating or six-face textures, a unit sphere, a pyramid, and a cylinder that I added, which I use for the custom candles that I set up. And then after declaring model types, I define the matrix SRT for any static and singular objects to be sent in during object creation to define their positions. And then here I get into some of the helper methods. They're really just organizing placement. Some are hard-coded like the inner trees and spotlights, and others are more grid-based like the fences and tombstones. But one that's actually doing something more dynamic is the generate background tree positions method. This one is basically responsible for scattering trees around the outside of the graveyard without me manually placing all of them. I pass in how many trees I want, and then an outer area where they're allowed to exist, and an inner area that I explicitly avoid, so nothing is too visually random within the graveyard, since I control those manually right here. And then I will get into this function now, I guess. So inside the function, the first thing I do is clear the list so it starts clean. Then I set up an attempt counter so we don't get stuck in a bad loop, and a minimum spacing value so trees don't stack on top of each other. From there, it just loops until we've placed enough trees. Each loop I randomly pick a X and Y position inside the outer bounds, then immediately check if it landed inside the inner no tree zone. If it did, I just skip it. Then I do a second check against all previously placed trees. I basically make sure, is this new tree too close to any existing one? Instead of using full distance, I just compare distance squared to keep it lightweight. If it's too close, I skip it again. This keeps the trees from clumping or overlapping and makes the spread feel more natural. Once a position passes those checks, I don't just drop it at a fixed height. I actually sample the terrain using a getHeightAtXZ function. So instead of guessing where the ground is, I can ask at this XZ position, what's the terrain height? And then I will also get into how this works as well. There we go. So the getHeightAtXZ function works by converting the world position into the terrain's grid space, clamping it so it doesn't go out of bounds, and then it grabs the closest height value from the height map. Right now it's using nearest neighbor sampling, so it's not interpolating between points, but for placing objects like trees, it's honestly more than good enough. And then stepping back, here we go. Then I take that height and I offset it slightly so the tree sits sunken in the ground a touch, and then I store it in a transform. And later on I just loop through that list and render the same tree model at all those positions. So this saves me from manually placing 100 trees and helps give the scene some variation in life. The next helper method is generate inner tree positions, which is way more straightforward than the previous method. Instead of scattering trees, I just manually define a few positions inside the graveyard to get a more intentional layout. With this method, I clear the list and then push back a handful of transform matrices with hard-coded positions. This lets me control exactly where those trees go, so they frame the scene nicely instead of relying on randomness. The next helper method, generate spotlight positions, is similar to the inner trees positions. But now I'm defining both positions and directions for each spotlight. So I clear two lists, and then for each light I push a position and direction vector. Most of them are angled downward with a slight offset, so they act like overhead lights or moonlight hitting the scene. Second to last is generate fence rectangle positions. This one builds out the fence around the graveyard using a few simple loops instead of placing each piece manually. I start by clearing the list and then defining some constants like scale, spacing between fence pieces, and rotation values depending on which side of the rectangle we're on. Then I split into 4 sections: front row, back row, right side, left side. For the front and back, I loop across the x-axis and just space them evenly. For the sides, I loop across the z instead and rotate the fence so it lines up properly. Each fence piece gets a full world transform built in the SRT format, so I can reuse the same fence model and just transform it into place for each section. And then on the right side of the fence, I skip a couple indices to leave a gap so it can act as an entrance to the graveyard. Finally, the last helper method, generate grave grid positions. This method lays out the tombstones in a grid using rows and columns, starting from a given XZ position and spacing them out evenly. One thing a little different here is the custom 2D height offset array. Instead of sampling the terrain like I do with the trees, I manually tweak the Y values per grave to better match the terrain shape. This was something I set up before I had the getHeightAddXZ function working, so it's kind of a handcrafted small scale solution to get them sitting nicely on the rough ground. I added some slight rotation variation using a simple seed based on the row and column, so the rows aren't all perfectly aligned and look a bit more worn. One downside is this setup is a bit touchy. The height offset array is specifically built for the 4:6 grid size and the current height map position. So changing the grid size or position would need adjustment to that data. So it's mostly structured placement, just with some manual offsets and variations to make it fit the terrain better. After defining all scene constants and positions, we finally get to make all the graphic objects that we're going to be using for the scene. For each object, we create a texture reference and pass that in, while also setting the desired material properties for each object. We have the crate, mausoleum, 4 tombstones, sharing 2 textures, 1 fence, and then the 3 components making up the candle model, the tree, and then the various demo objects, which include the dice, sphere, pyramid, and cottage. And then one thing to note is any static or one-off objects are set to worlds in a demo, and then all other objects are looped through when we place them in the draw scene. And then the camera I did tweak as well to increase the FOV slightly, just because I increased the size of the viewport, so the scene was a bit easier to see. So within the update scene, I have 2 helper methods to update the positions of all of our moving lights in the scene. So the first method, update moving lights. This method updates the positions of my moving lights every frame. Each light has a predefined center point inside the function, and instead of keeping them static, I apply a small offset to move them around that point. For each light, I take the total elapsed time and scale it by a speed, and then use sine and cosine to generate a smooth figure 8 motion, so the lights are drifting around their center positions. Each light uses slightly different speeds, sine cosine combinations, and movement scaling, so they don't all move the same way, which helps sell that more mystical, spooky vibe of a graveyard. Then I update the light positions in the array using that offset, while keeping the Y value fixed so they stay at the correct height. And then this array of candlelight positions is fed during the draw scene into both the render method and the add point light method with a slight offset so the candles and lights move in tandem. And then the second method, update demo light, is basically the same idea as the other moving lights. Just simplified down to a single light. I define a center position and then use cosine and sine over time to move the light in a circular path around that point. This one's mainly for demonstration, showing that the pile of demo objects respond to a dynamic light. So finally in draw scene, this is where everything gets brought together and actually rendered to the screen. At the start, I clear both the render target and the depth buffer, so I'm working with a fresh frame. Then I get the camera position and send the camera and view projection matrices into my shader texture light, since the shader needs that information to calculate lighting correctly from the player's point of view. After that, I clear out any previous light data, stored in the shader and rebuild the full lighting setup for the current frame. The first thing I do here is calculate a candle flicker value for each candle using sine over time. That gives me a few different brightness values, so all the candle lights are not flickering in sync. Then I define the mausoleum candle positions by taking an offset and transforming it by the mausoleum's world matrix, so that light is positioned relative to the mausoleum instead of just hard-coded in world space. And I use that offset eventually to further place a group of candles in a similar position. From there, I start adding lights into the scene. One directional light for moonlighting, and then all of the spotlight beams using the position and direction list that I set up earlier. And then the 3 moving candle point lights using the array from earlier. The mausoleum candle light, which I only put one point light for the small group of them. And then the demo area candle light, which also uses the dynamic moving array, or not array, just position. Once all of those are added, I send the full light parameter into the shader, and then I also send the fog settings that were defined earlier in init demo. So by that point, the shader has everything it needs for the frame: camera data, light data, and fog data. After the shader setup is done, I start rendering actual scene objects. First, the terrain and skybox get rendered. Then I move into the main scene objects like the crates and mausoleum, and then the small group of candles using the mausoleum positional offset. And then for repeated objects like the trees, I just loop through the lists that we set up earlier and render the same model at each stored position. But there's extra work being done here in the render tree method, which I will get to later. Then I render the demo objects, the grave grid, using the position list from earlier, which this also just loops through. Oh, I guess I didn't cover, well, I'll get to that later eventually as well. And then, yeah, same idea for the fences, but these don't randomize. And then, yeah, render candle for each of these, which I will also get into because this sets up the custom candle model placement as well. So overall, draw scene is really the final assembly step. By this point, all the positions, transforms, moving light updates, and scene setup have already been handled earlier. And this function just takes all that prepared data and sends it into the shader and renders the final frame in the correct order. So now to work back through the draw scene and go through any specific helper methods that I set up. So starting kind of randomly with render crate down here. This one just kind of simply, it's kind of like the most basic one, I guess. Don't have to explain it too much, just sets the world and renders it. But it, I don't know, just helps clean up the draw scene a little bit. And then the kind of spicy one, I guess, render candle. This one builds and renders a candle using 3 separate cylinder meshes instead of having a full candle model. I construct it manually using a base, the body, and the wick. First, I create a parent transform based on the input position that basically acts as the anchor point for the whole candle. Then each part I scale to the right shape, apply a small offset so it sits in the correct spot relative to the base, and multiply it by the parent transform. So everything stays grouped together and moves as one object. The wick also has a slight rotation just to give it a bit of variation, so it's not perfectly straight. And then just to kind of go back over some things, to kind of show off the mausoleum candle offset positions. This is what it's kind of doing. The lit candle is the one that's colored, I guess. And then I offset these other candles based on that position. And then there's just the light here. And then, oh yeah, sorry, I forgot to show the actual candle model up close. Basically, it's just a flattened cylinder, a tall cylinder, and then a tiny cylinder on an angle. So the next helper method I was going to talk about is render tree, which I had to make some quick changes because I realized we were calling a bunch of randomization logic every frame, which is no bueno. So I shifted the randomization to the generation position methods. And basically what this does, this method, uh, it extracts the x and z position from the transform and uses that to build a deterministic seed. And instead of fully random values every frame, well, actually that's fixed now. Yeah, it used to freak out all the time, but this will just give it anyways consistent random values. Yeah, so there are a few small random offsets. There's a slight scale variation, random rotation on the y, and a small tilt on the x and z. So each tree ends up looking a little different even though they all use the same model. Then I combine everything together with scale, tilt, rotation, and then the original position. And then I send that to the final transform for the tree object to be rendered. And then, yeah, now this is in the generation logic, so this is only called once in the init demo and not for every object, every frame, which is very expensive. And then moving into the light helper methods, the first one I will go over is the add moonlight. This is just a small helper method that wraps my shader's add spotlight call. Instead of passing all the parameters every time, I just pass in the position and direction, and everything else is preset. All of these values are tuned to give a soft moonlight/beam effect. It has a large range, subtle attenuation, a slight bluish diffuse color, and a wider spotlight angle. So every spotlight ends up looking consistent without me having to redefine all those values every time. And then the next one right here is kind of the same thing, but for candle lights using the add point light. So instead of hard coding everything, I pass in the position and the diffuse color, and the rest of the values are preset. The main thing is the diffuse values change per light, so I can pass in different flicker values that I calculated earlier, which makes each candle pulse slightly differently. Everything else like range, attenuation, and ambient stays consistent, so all the candles feel like the same type of light. So the next method to talk about is render grave grid. This method just loops through all the pre-computed grave transforms and then renders them. At the top, I store 4 tombstone objects in an array, so I can easily switch between them. And then inside the loop, I calculate the row and column based on the index. And then I use a simple formula to pick which tombstone model to use. So instead of placing them in a fixed pattern, it gives a bit of variation across the grid. Then for each position, I set the world transform for the list and render the selected tombstone. The last helper method to talk about is the render fence rectangle. This one isn't anything fancy either, it just loops through the list and then sets the world based on the preset list we have earlier. So for the fog, the actual blending happens in the pixel shader, but before that I needed a way to send the fog settings from CPP into the shader. So inside of shader texture light.h, I added a small fog data struct that stores the fog color, where the fog starts, where it reaches full strength, and the maximum fog intensity. I also added a dedicated constant buffer pointer, MP fog buffer, so the shader has its own place to receive that data. Then in the shader light constructor, I create the fog buffer just like the other constant buffers. It's set up as a dynamic constant buffer, which means I can update it from the CPU during runtime. The buffer size is just size of fog data, so it matches the structure exactly. Then in send fog parameters, this one, I map that buffer right in the current fog values and unmap it. So this method is basically the bridge between the CPP scene setup and the shader. It takes in the 4 values and copies them directly into the fog data struct that the pixel shader reads from. The extra fog padding is there just to keep the struct aligned properly for the constant buffer layout. Then once that data is in the shader, the pixel shader can use it after lighting is finished. It calculates the distance from the current pixel to the camera, maps that distance between fog start and fog end, clamps it with saturate, and then multiplies by fog max. After that, it uses lerp to blend between the fully lit pixel color and the fog color. So nearby pixels stay mostly untouched and farther ones gradually blend into the fog. And then right here is the guard if the settings are incorrect. And then one other thing I added to the point and spotlights in the .hlsl file here is this range-based fade, just to avoid harsh cutoffs. Normally, the default lights have a hard range where they just stop affecting anything past a certain distance, which can look pretty abrupt. So after calculating the distance from the light to the pixel, I compute the range fade value. It goes from 1 near the light down to 0 as it approaches max range. Then I square it to smooth it out a bit more. That fade gets multiplied into ambient, diffuse, and specular. So instead of the light suddenly cutting off, it gradually fades out as it reaches its range.